Today what we're going to be doing is we're going to be learning about the terms of permanent magnets, electromagnets, magnetic induction. We're also going to talk about how permanent magnets work and how electromagnets work. We'll also talk about the Earth's magnetic field and how that deals with magnetism itself. And then lastly, we're going to talk about induction. So magnetism. Uh, these first few slides and notes will be relatively simple. Permanent magnets are very simple. We already have an intuitive knowledge. You probably have learned it in elementary school, so it's not going to be all that fascinating. Electromagnets, on the other hand, we're going to start introducing. It will be a lot more, but it relies on this stuff beforehand. So we're all familiar with magnets, and they have two poles, a north and a south pole, and that the opposite poles attract and the like poles repel. Nothing new. And every magnet has two ends, these poles, and with those poles you can actually look and see what we call the field lines. They produce these invisible lines of magnetism, and they send out these magnetic fields, and we call them field lines, and this is where the strength of the magnet comes from. It shoots them off from the poles and goes to the other pole, kind of in a loop-like fashion. Now, the more fields, the more lines there are, the greater, the stronger the magnet. When they're closer and when they're smaller, weak, thinner, then that means they're more further apart, the weaker the magnet is. So this is kind of a representation of that magnet as these field lines come out and they're strongest at the poles, weakest in the middle. So they now notice the compass here. The compass's north tip of this compass is pointing south, because remember, the North Pole seeks the south. This is weird because our northern hemisphere, our North Pole, is actually the south pole of the south magnetic pole of the Earth's the north pole of our Earth is actually the south magnetic pole, because the north point of a compass points to the north. It's kind of weird to say, and it's hard to say, and that's because the field lines will follow to the south. So it's kind of weird to say. Now, what causes magnetism? Well, in permanent magnets, you get little moving electrons, and they have a magnetic property. And because of this, magnets, in most materials, these magnetic fields can cancel each other out. But if you added a magnetic field force, that's what these lines, they kind of line themselves up. And that's why if you attach a piece of a magnet to a piece of metal, all of a sudden the whole piece of metal becomes magnetic. And that's because you're lining up all those electrons with each other, and they all kind of point in the general direction, making an overall magnet. Now, the only other materials that are common, everyday materials that can be magnets, what we call permanent magnets or ferromagnetic, are iron, cobalt, and nickel. And that's because each little atom acts as a magnet. They also have crystalline structures. This is the reason why why iron isn't always a magnet. And that's because in the crystalline structure of a piece of iron, where you'll have a little crystal that has a magnet pointing down, to the right, to the left, sideways, forwards, backwards, whatever, it's all random. And those little crystals kind of overall cancel each other out, so the whole piece, like a paper clip, is not magnetic unless a magnet comes nearby and forces all these what we call domains, these little tiny crystals, to shift their magnet moments all in one direction. Now, there's a great video, and I'll let you just look it up. We won't watch it on this video, but it's called Minute Physics. If you type in Minute Physics into YouTube and then type in magnetism, there are two videos that are great at discussing about magnetism. And the Minute Physics talks about why permanent magnets, and it goes into a lot more and a lot greater, better detail about this. So if you cut a magnet in half, you create 2 magnets. If you cut it in half again, you create 3. In fact, you can go all the way down until you get to the single electron. So our Earth, like I said earlier, is a big magnet. The core is probably composed of iron or nickel. That's what we think the core is made out of, and we think that because the liquid core is going around the Earth, this is creating an electrical currents which result in a magnetic field. And that electrical field pushes off. Now, realize that the magnetic North Pole is actually the south, or the North Pole is actually the southern magnetic pole, which is kind of weird to think, but remember the compass North Pole points to the North Pole, and and that opposites attract. So this is kind of the weird thing about it. And also, true north is not where the magnetic north. So if you were to follow a compass all the way up to the North Pole and just kept going, you would get to a point where you would actually be several miles, hundreds of miles away from true North Pole. So, the magnetic field itself expands into space, and we call it the magnetosphere. It's part of the atmosphere, and the job of it is to protect the Earth from particles from the sun, called solar winds. They will strike our magnetosphere, and they bend around, and some of them get sucked into these vortexes and pulled in, and if they hit this, we call them the northern lights. So the aurora borealis, or the northern lights, is created because of that trapping all that atmosphere, pulling them up into the northern hemisphere. There is southern lights down in Antarctica. We call them the aurora australis, and that happens in the southern hemisphere. So if you ever want, you can look up some good videos, and then you can watch some videos about the southern hemisphere, or the northern lights and the southern lights and the auroras and the causes of them. There's great videos online about those, and they're gorgeous, pretty. Now comes into electrical currents and magnetism. Okay, in 1820, a Danish scientist, Hans Christian Ørsted, discovered that if you put a wire next to a compass and turn on that wire with electricity, and by the way, this was just when batteries were just invented by Voltaire, and so he was playing around with this brand new thing, and he realized that the compass needle deflected, and it was weird. This was then shown to his fellow colleagues, and another gentleman by the name of a British man by the name of Michael Faraday demonstrated, and he proved that there was some magnetic field being produced using electricity. This was weird. Faraday is considered the father of electricity, and this is kind of Ørsted's thing. He had it opened, he closed it, the needle deflected. And then he's like, wait, let's switch it around. Let's flip the current the other way. Well, then it flipped the opposite direction. It was weird. It didn't make sense. So he continued on and did more, and Faraday's the one that proved, using actually this very similar thing where he put a wire vertically and he traced out and proved that there's these circles of magnetic fields coming from an electrified wire, proving that electricity makes magnetism. Now, if you take a copper wire, which is not magnetic, pass a current through it, it becomes a magnet. And if you coil it, then it becomes a traditional bar magnet. The field lines look and act identically to this. And we call this the electromagnet. Now, electromotors are ways of where we use electromagnets to convert electrical energy into mechanical energy. So a motor has two working parts. There's a stationary magnet, and then we have a movable copper ring. This is referred to as, we call it the armature, but it's basically a movable copper ring. And if you move the copper ring with a current traveling through it, it's going to spin that ring. Now, electric motors And then you have electric motors and then electric generators. Electric generators is just the opposite direction. This is where it's taking mechanical energy and turning into electrical energy. So like the Hoover Dam spins that armature, that copper ring, or a magnet, it could either be either one, and that pushes electrons through the copper ring, the copper wire, producing electricity. So now we get to the last little bit, and that's called induction. This is when you pass a current through it. It's going to not touch, but it's going to push electrons through it, and then it's going to cause and induce a voltage. And if depending on which direction you go through, it's going to go either in the positive direction or a negative direction, or either the electricity is going this way or backwards. This is called inducing a current, and so that's what's happening with generators. Now, the magnitude of these voltages is determined by the number of loops, the strength of your magnet, and how fast, or the rate of the magnetic field line, cuts those wires. So like as they travel through it. So we could use this in DC and AC generators, and we also have in transformers, not the robots, but the little cylinders that are on your power lines. So when electrons flow through a wire, it produces magnetic fields, and when the electric fields move perpendicular to the magnetic field, you produce light. What does this mean? Well, you have a magnetic field going this way in the x-axis in a wave-like fashion, and that is the actual medium for an electric field to move up and down, which is the medium for a magnetic, so it's self-propagating. This is how light works. This is why light doesn't need a medium, because it has its own medium. So when electrons move through a wire, it produces light. And that's it. If you have any further questions, please go ahead and ask your teacher.